In this video, I'll demonstrate how a mid-century bungalow is transformed into a modern family home, and I'll show you how this home meets a combination of financial, quality and environmental objectives. We'll first consider what size home the owner can afford with a budget of $600,000 using a simple square metre rate cost estimate. Next, I'll critique the structural design and emphasise the importance of adopting simple structural systems constructed with speed, underpinning the success of any project. The next objective is to ensure the building's shape and orientation is arranged to harness heat in the winter, shelter from it during the summer, and coupled with this, airtight construction that boosts the overall thermal performance and reduces gas and electricity bills. I'll conclude by illustrating how the design achieves a strong connection with landscape, flexible and flowing accommodation, as well as spaces of comfort and quality. Thanks for tuning into Design Construct, where we deep dive on topics covering design, planning, construction and many more, helping homeowners manage their project better and set up for success. So, the underlying success factor for many homeowners is to establish and maintain cost and time certainty, as well as ensuring good value for money. With this in mind, let's first consider roughly what size home the owner can afford with a budget of $600,000, this sum to include professional and authority fees. We'll use a simple square metre rate cost estimate. So the site's area is 270 squares and the permissible floor space ratio is 0.7, which means the maximum legal size house from a planning perspective would be 190 squares. Let's assume construction costs of $3,000 a square metre. This amounts to $570,000 for the building alone, and we'll add another $90,000 to cover professional and authority fees and a little contingency. This brings the total project cost to $660,000 all in. So straight away we've exceeded our budget by $60,000. Our options to steer costs back on budget are to either reduce the professional fee allocation, reduce the assumed construction rate of $3,000 to say $2,700, or we could shrink the size of the house by about 20 square metres. Now, a key part of any project's success is to find and engage the best possible consultant team and draw as much of their expertise and knowledge as possible and capture this during the design phase. If design and documentation is carried out to a high standard, this will translate into robust and reliable quotes from builders, as well as a faster build time, because good designers will have speed and buildability at front of mind when designing. So for these reasons, we'll leave the budget allocation for professional fees and instead we'll reduce the size of the house by 20 square metres. Let's discuss the square metre rate, influenced by many factors. First, the fact that this is an addition as opposed to a new build. We'll need to account for making good the existing building, renewing existing services, and the time required to carefully deconstruct the rear portion of the site to allow the new portion to tie into it. To account for these works, I've applied the same rate of $3,000 a square metre to the portion of the house that is retained. This is erring on the conservative side. Second, are the structural systems. To achieve good value for money, the structure needs to be simple and fast to construct, so your average builder can confidently procure and construct, attracting as little contingency as possible for time and cost. In this example, the engineer has specified a slab on ground founded on concrete piers. The shape of the slab is simple and absent from deep folds and set downs that require more formwork and reinforcement and potentially multiple concrete pours. A compact footprint is also key, minimising the cost of expense of civil and structural trades. Simple homes usually require one pour for the piers, then a second pour for the slab a week or so later, each typically needing a pump and boom and possibly traffic management, all adding to the overall costs. Now next is the structural steel, comprising several columns and beams. This is a manageable amount of steel in a relatively simple setup that is typically installed using a crane. With careful forward planning, a good builder will be ready to load the job site with a heap of other materials, maximising the use of crane, reducing labour costs and generally pushing the program along. Okay, so after the steel, the structural timber frame is built. There are load-bearing walls from studs, the upper level floor from joists and the roof from purlins. Floor spans need to be carefully considered, as the costs for joists and purlins increase disproportionately as the span increases. Limiting spans to 5 or so metres allows for smaller section sizes that are quick to assemble with fewer carpenters. Larger spans require large sections that are deeper, heavier and harder to install. For this home, we've adopted wall heights of 2700 at ground and 2550 at level 1. These dimensions align with standardised sheet widths supplied at 1200 and 1350 and are typically installed horizontally, one above the other, avoiding offcuts and saving on skip fees that amount to thousands of dollars. With these key spatial dimensions considered, we can start resolving the building's shape and orientation to maximise heat gain in winter and shelter in summer. Let's take a cross-section through the building and examine the sun's altitude angle on the two most extreme days of the year, being the 22nd of December and the 21st of June. At 12 noon, the angle reaches 75 degrees in summer and 29 degrees in winter. In summer, the level 1 mass comfortably blocks the sun. In winter, several metres of sun enters the house and heats the concrete slab. The radiation from the sun will be absorbed in the concrete's mass, then emitted as heat during the night, saving hundreds of dollars in heating costs in a year. Another component to this heating strategy is to specify a glazed unit along the full width and the height of the northern wall, as well as using carefully positioned deciduous trees. Now, heat gain to the upper level is controlled using eaves that are typically 450 deep or 600 deep, half the width of a standard sheet of fibre cement. If there are no eaves, it will be blocked as it sweeps through its azimuth angle during the day. These are basic shading measures that are a statutory requirement throughout Australia. Let's now consider the eastern elevation, where the sun's altitude angle gets to be as high as 75 degrees in the summer months. The sun's heat penetrates all morning, effectively baking the interior of the house if not properly protected. In this scenario, operable vertical louvers have been specified that block the sun's UV rays while allowing sunlight to enter. It's important these louvers are vertical and located on the outside of the building, so radiant heat is kept outside. In the winter months or during the evenings, the louvers are retracted, allowing heat and light in and restoring views to the garden. Now, the same design response is applicable to the western elevations. And in addition to louvers, low E glass could be specified to further reduce radiant heat transfer, having a very thin coating applied to one side that reduces the transfer of heat or cold through the glass, acting as an invisible insulation barrier. Now on the topic of thermal performance. Probably the single most important factor after building orientation is the airtightness of a building. Airtight buildings have much lower space heating and cooling requirements and allow air movement to be controlled depending on the season. Let's examine the house in the longitudinal section and visualise how thermal stratification occurs naturally during the summer months. In this example, vents are positioned in the roof and upper level, allowing the hottest air to trickle out, while another vent is located at the lower level, allowing cool air from under the house, that's the original part of the house, to be drawn in. This is passive cooling without the need for electric fans to draw or push air. The success of this system depends on how airtight the building is and how well other parts of the building are insulated. If construction is executed well, the occupant could remain comfortable well into the afternoon on a summer's day before switching on air conditioning. During the winter months, those vents would be shut and the heating strategy would involve harnessing energy from the sun, as we demonstrated earlier, and storing this heat in the thermal mass, slowly emitted as radiant heat into the air inside the house. An airtight building will help contain this heat inside for longer, allowing the heat generated by bodies and electrical equipment also. Let's now explore how the design creates a strong connection with landscape. Essentially, the shape of the floor plan has been articulated, combined with full height and full width operable glazing, so the occupants can visually and physically access and connect with the landscape from all key living spaces. If you look closely, two slender windows have been located on the southern elevation, which will allow indirect light to enter, but also creating further connection with the sky. This window is operable, promoting cross ventilation and contributing to better indoor air quality. Ceiling fans are another obvious means to promote airflow. Let's now examine the spatial arrangements in some more detail. One important observation is the direct adjacencies between the kitchen, dining, living and the courtyards. Depending on the occupants and the occasion, different combinations of spaces have the capacity to work together. For example, the adjoining courts becoming an extension of the kitchen or the living room, allowing the dimensions of the internal rooms to be a little smaller without compromising the feeling of space and comfort. To achieve this, material selections and detailing would need to be carefully considered to improve the flow between the internal and external space, helping connect and unify the two. Another combination is the kitchen and dining space during meal times, or the living dining space where occupants may be interacting. Another important feature on this floor plan is the operable sliding door separating the living and dining, effectively creating two distinct zones that are visually and acoustically separated, providing further flexibility. So that brings us to the end of this video, folks. If you want some tips on designing a luxury bathroom at an affordable price, check out this video. Thanks for tuning in to Design Construct. Please hit the like and subscribe button, and I'll see you at the next video.